Okay, science notes topic 10 and 11, part 3. We're talking about efficiency. So when we talked about the laws of thermodynamics in this unit, we talked about how energy can't be created or destroyed, it can only be converted, and that nothing is ever 100% efficient. So that also applies here, right? So that's where we get this first statement: no electric device we encounter is a perfect energy converter or 100% efficient. If a light bulb was 100% efficient, all of the electrical energy took in, which we refer to as the input energy, would be converted into light energy, which is the useful output energy. Because there's other output energies as well. Usually when you turn a light bulb on, there's a tiny little bit of sound. There's a bunch of heat, right? So those are also output energies, but they're not useful. It's not what the device is actually designed to do. So only the light is the useful output energy. From experience, we know that this isn't true. Light bulbs definitely convert some of their input energy into heat as the bulb gets hot. We can express efficiency as a percentage with the following mathematical relationships. So efficiency is equal to the useful energy output divided by how much energy goes in, or the energy input. And then because that's going to turn into a decimal, we multiply by 100% to get it as an efficiency in percentage. So like 70% or 80 or whatever it is. Okay. Short form, if you want to write this so it doesn't take as long, we do EFF for efficiency, capital E out, capital E in, and then times 100%. So that's an easier, quicker way to write it if you're writing the formula. So if we are given the amount of energy supplied to a device, that's always going to be our input energy. That's what's going in. And then if we're given the useful energy it produces, we can calculate the efficiency. So a hairdryer supplied 48,000 joules of energy. So because this is supplied, we know that this is the input energy. It only converts 22,500 joules of energy into useful heat. So because this is the useful energy, this is the energy that's going out. Sometimes the hardest part about these questions is figuring out which one's in, which one's out, okay? Input should always be bigger than output. Otherwise, you're getting more than what you put in, which is more than 100% efficient, which can't happen. Defies the laws of physics. So always think about supplied or put in, or if you've plugged something in and that's what it's getting out of the wall socket, that's always going to be your input. Always think about what's useful as your output. And then the rest is lost to sound, because we know hairdryers make a lot of noise. What is the efficiency of the hairdryer? So efficiency is equal to energy out divided by energy in times 100%. So we're going to have 22,500 joules over 48,000 joules, and then times 100%. Notice how the joules divided by joules cancel, and that should always be true. So your units always need to match. If you're using joules, use joules. If you're using kilojoules, then they need to match, those sorts of things, okay? Then we do this division, we multiply by 100, and we get, because if we just did the division, we'd get 0.469, blah, 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 okay? Then we multiply it to 100, or by 100 to get a percent, so we get 46.9%, okay? Often we will need to calculate the amount of power that's supplied to or produced by a device, drawing on our knowledge that energy equals power over time. So it's not always going to give us how much energy goes into a device. So sometimes we need to calculate that first and then use our efficiency formula. So an example of that might look like this. A 1,000 watt electric kettle takes 4 minutes to boil some water. If it takes 196 kilojoules, which would be the same as 196,000 joules, to go from kilo to just joules, we multiply by 1,000 of energy to heat the water. What is the efficiency of the kettle? So the first thing we need to do is find the electric energy input to the kettle. So if you're ever using E equals P over T, this is always going to be energy in, right? So if it's power times time, that's how much is being provided to the device, okay? So power in this case is 1,000 watts, right? That's right here. And then time is 4 minutes. Now I can't just plug 4 minutes in here. I need to convert that to seconds. So we know that there's 60 seconds per minute times 4 minutes. So 4 times 60 is 240 seconds. So that's what I'm going to plug into my energy equation. So then I get 240,000 joules of energy, okay? So either, because this question gave me 196 kilojoules, I can either convert them both to joules, or I could have converted this by dividing by 1,000 into kilojoules. So this would be 240 kilojoules. So as long as I use the two that match, I can use either. So I could use like this one and this one, or I can use the two in circles in my efficiency equation. They just need to match. Notice how this one is higher than this one, okay? So this is my energy in. The other way I know that this is output is that it's the energy that's actually accomplishing what the kettle is supposed to do, right? It takes 196 kilojoules of energy to heat the water, right? That's what a kettle's for. And then the rest is being used for sound, and maybe there's a little bit of light in the kettle, those sorts of things. Maybe it has one of those little flick up and it glows blue, that kind of thing, okay? So to find the percent efficiency, we're going to go efficiency is equal to energy out divided by energy in times 100%. Formulas will always be given to you, so you don't need to worry about memorizing them. And my energy out is 196 kilojoules. My energy in was 240 kilojoules. Now this would be the same as if I used both of these numbers with joules instead. So either way you do this calculation, you're going to get the exact same number. Oops, still need to multiply both of them by 100. So either way, we get 81.7% no matter which way we do the calculation, right? Make a little note for yourself that units need to match. So there's how we do efficiency. Okay, so if you guys have any questions, you can always pause, rewatch these videos, and then any questions can be directed towards any of us science teachers if you come across them.